Let's study slightly more. Now let's study a slightly more elaborate example of the third-order differential equation. So here it is. The task is as usual. Find all the solutions, normalize them by the standard condition at the origin, and find all the asymptotics at z tending to plus and minus infinity. As usual, we write down our p and q polynomials. And compute all the integrals which define the structure of our exact solution. And here we go. Our z of t function is simply e2 minus t cube over 3, 1 over t2 beta. And the v function, which seals the position of the contour, is almost identical. Sorry. So the v function is e2 zt. Now let's write down the exact solution in terms of the contour integral. And let's study its structure. So we draw a complex plane of variable t. And the first thing we notice, so beta factor is arbitrary. So v and z functions are multivalued functions. So in order to define them, we need to draw a branch cut. Well, it's up to us to choose this direction. Let's choose some standard thing. So from plus infinity to 0. Next, let's study the structure, the convergence of our v function. Well, it's quite a typical type of expression. We encountered it many times before, for example, in the theory of Airy function. And at large t, v function is dominated by this exponent, e2 minus t cube over 3. So basically, if you want to study the regions where v function vanishes, we just need to solve the following algebraic equation. The real part of t cube should be positive. And that means that the cosine of the argument of t, or the triplet argument of t, should be positive. So you can solve this algebraic trigonometric equation. And what you get is the following regions. So the first region at the angle from minus pi by 6 to pi by 6, and so on and so forth. So the second regions are symmetrical. Right. Now let's study the possible placement of the contours. Well, since these are the regions where our contour could start and end, one of the most obvious placement would be as follows. So the first contour goes from infinity in the second quadrant and continues to infinity in the first quadrant. So let's call this gamma 1. The second contour, say, starts from plus infinity in the fourth quadrant and continues to infinity in their third quadrant. Let's call this gamma 2. And finally, their third quadrant starts at at infinity in the third quadrant and continues to the infinity in the second quadrant. And let's denote it by gamma 3. So those are three linearly independent solutions. Obviously, they can't be deformed smoothly into one another, and one can't compose a linear combination of these contours to get the zero contour, right? So due to the presence of this branch cut. So these are all linear independent solutions. Right. So now let's study let's normalize all of these solutions. So we have our normalization condition, and let's compute our function and at z equals to 0. The integral is simplified. And here we have quite a typical situation. So the integral initially is taking along some complicated curved contour, but in order to get the exact value for our integral, we can deform the contour in such a way that the integral is simplified. For example, let's take contour gamma 1. Obviously, it could be deformed into the combination of two straight lines. And the question is, what would be the best possible placement of these straight lines to simplify the computation of the integral? Well, first of all, we see that the integral is taken from, say, 0 to plus infinity, then it's just a gamma function. As long as the exponent is a purely real number, then the integral is very easy to evaluate. But let's actually find out the arguments of the exponent such that of t variable such that the exponent is a real number. So t is equal to the modulus of t times e to I phi. So t cubed has the argument 3 phi, and if you want the whole thing to be real, then our 3 phi should be equal to 2 pi n. And here are the possible placements of our directions. So phi equals to 0, or phi equals to plus minus 2 pi over 3. All right. So the first phi is equal to 0. Well, that was obvious. That's just a straight segment from 0 to plus infinity, and the integral is reduced to gamma function. The second segment is pointing in the direction to pi over 3. So it's median of this angle. And now we have the idea. So we deform the contour in such a way that it becomes a combination of two straight lines. The first one is the horizontal, and the second one is inclined by 2 pi by 3. And this way, the whole integral becomes a contribution of two gamma functions. The first one is from 0 to plus infinity. For the second one, we introduce this parameterization. T equals to rho to e to 2 pi I by 3. And t cubed, again, would be minus rho cubed over 3. D rho from and d rho e to 2 pi I by 3 divided by rho to beta plus 1 e to 2 pi I by 3 beta plus 1. Okay, that's for the second piece. And for the first piece, is simply the integral from 0 to plus infinity. Oh, sorry, from plus infinity. No, from 0 to plus infinity, of course. From 0 to plus infinity. e2 minus t cubed over 3 dt over t2 beta plus 1. And here, since we go from infinity to 0 and then from 0 to infinity, here, of course, we should put additional minus sign, because initially the integral is taken from infinity overall, from infinity to 0. Right. So after a simple change of variables, say t cubed over 3 equals s, the integrals are reduced to identical gamma functions. And with your permission, I just give you the answer for this integral. And the answer is as follows. So it just, right, it's 2 pi I and we normalize the integral by the following condition. Of course, here I use the mirror identity for the gamma function, because initially gamma function appears in the denominator, and then with the help of mirror identity, we put it in the denominator. This just makes things a little bit more elegant. And so we perform each calculation for that kind of calculation for each of our contours, gamma 1, gamma 2, and gamma 3, and arrive at the correct normalization factors for our solutions. And let's continue with the next slide, where we investigate the asymptotics of the corresponding solutions.